All right, so we are going to be talking about electricity today, and I wanted to start with two terms that we already know and that we're going to see again today. When we talked about heat transfer, so heat moving from one thing to another, we talked about conductors and insulators. We're going to see those terms again today, but we're going to be talking about them conducting and insulating electricity this time. So today's notes are actually 3 sets of notes that I have squished into one. So I'm not going to go in depth with anything, but I do want you to have kind of a general knowledge of what's happening with electricity. So the first thing is, if we're going to talk about electricity, we need to talk about where those charges come from. So atoms have positively charged protons and negatively charged electrons, and those positives and negatives interact with each other. So if I have two same charges, so two positives or two negatives interacting with each other, they're going to repel, they're going to push away from each other. On the other hand, if I have opposites, so a positive proton and a negative electron, they're going to attract to each other. One other thing that can happen is if you have something with a charge and something that doesn't have a charge, they'll be attracted to each other as well. And these forces change depending on distance. So if I bring two of those things close together, I'm really going to feel that attraction or that repulsion. It's kind of like if you've ever played around with magnets. The closer I bring those magnets to each other, the more I can feel that magnetism. Same thing with electric charges. So if they're close, I can feel it really strong. If they're far away, I'm not going to feel it in the same kind of way. So the first thing we're going to talk about is static electricity, and this is just built up charges in something that then can transfer to something that doesn't have that charge. So in the picture on the left, you can see that the static electricity from the packing peanuts has ended up on the cap. So now they're statically charged together. You can see it on a much bigger scale as well with lightning. Lightning actually builds up a charge in the cloud and then transfers that electricity from the cloud down to the ground. That brings us to our law of conservation of charge. Now, this is our third conservation law of the semester, and they're all the same. All it's saying is I'm not creating an electric charge, I am transferring it. So, for instance, if I was that lady walking across the room and then touching the doorknob, she didn't make that charge. What happened was she had the charge and then she transferred it over to the doorknob. Now, there's 3 ways that you can charge up an object. The first one is like what I just described, walking across the floor, building that friction between you and the carpet. So friction is an example where you're walking, or you can see the picture of the balloon rubbing against your hair, and it takes the charge from one object and puts it on the other. The next one you don't really need to know quite as much about. It's induction. Basically, everything has to be lined up perfectly for that electricity to flow. So in the picture, you can see where they've got the pan. That is allowing that electricity to flow. Whereas the part that doesn't have the pan, you can see that the chocolate's not melting at all because that electricity is not actually flowing through. And then the last method for charging is one we're familiar with. We talked about it with heat transfer. Exact same definition here for conduction, just this time we're talking about transferring electricity through touch. So this is where insulators and conductors come back in. So conductors, like metal wires, allow electricity to flow, while insulators, like the rubber coating on the outside of wires, stops it from flowing. A new term for us is semiconductor, but it's got a familiar prefix to it. So a semicircle is half a circle. So a semiconductor is basically half a conductor. It kind of conducts electricity, but not really well. Now, All electronics have semiconductors in them, so no matter what device you're using to hear me right now, you have semiconductors like silicon and germanium in your device. And then you can probably guess from the name of this one, superconductors are conductors that are really, 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 really good at conducting electricity. Now let's talk about moving that electric charge from one thing to another. So first of all, electric current is the flow of electrons. And this can happen directly, where electrons just move from point A straight to point B. That's called direct current. That would be like battery operated stuff. The current that's flowing through your house is alternating current. It's still getting from point A to point B, but it's kind of doing a zigzag back and forth motion to get from one place to another instead of getting directly there like direct current does. The force behind electric current is called voltage. Now, electric current always flows from high voltage to low voltage, which is why you're supposed to be really careful if you see something like a downed power line, because it's a source of a lot of voltage. You do not have voltage, and so that electricity, if you touch it, will flow directly into you. And then the last part of it is resistance. Resistance are those things that you plug into a circuit that take just a little bit of electricity away. It takes a little bit of that electric current away. Every single thing that you plug into a circuit adds resistance. So that's why you're not supposed to overload an electric circuit. You can't plug in 75 things into one socket because you'll overload the circuit, because every little thing is taking away a little bit of electricity. So the combination of these three things together is called Ohm's law. So here, I really like this picture because it kind of shows what's happening. So you've got your current trying to flow through the wire, and voltage is there being the force trying to push that current along. But resistance, every single thing that I plug into the circuit, is slowing down that current and kind of taking a little bit of it away. So we have the equation voltage equals current times resistance. Now we get to the good news. We are not doing any math anymore. Yay, no more math. But I do think it's helpful to kind of look at it in relationship to each other. So if I increase my resistance, so the two equations I've got there, I'm going from 5 resistance to 10. Then if I was keeping my voltage the same, my current would go from 4 down to 2. So basically what's happening with that is the higher my resistance, the less current is flowing through. And if you look back at that picture, that makes sense. Couple other terms that I want to talk about. The first one is electric power. Now, if you've ever looked at light bulbs or microwaves, they have how much watts are in that device. That is the exact same watts that we talked about in Unit 3, which is power. So power is another way that you can describe the electricity needed to run a device. Electrical energy, on the other hand, puts time into it as well. So not only how much power are you using, but how many hours of the day are you using that device. So electrical energy is important because this is actually how people's power bills are figured out. The power company has a certain amount of money for every kilowatt hour used. They know how many kilowatt hours you use each month, and so that's how they figure out how much to charge you every month. The last thing that we're covering are circuits. So basically the loop of electricity getting from your power source to the devices that you're trying to turn off and on. You need to have a closed loop for the electricity to flow. If it's open, or if you have a switch that's open, or you have something that's missing, then it's called an open circuit, and none of the electricity will flow through because it can't make that loop. There are two major types of circuits. The first one is called a series circuit, and there's only one loop of electricity there. So the electricity can only go one certain way. The problem is if any of those light bulbs burn out, then the electricity can't flow through. So you've got an open circuit, and so none of the bulbs will work. In comparison, the other type of circuit, the one that we have in our homes, is a parallel circuit. This means that if a light bulb burns out, or if I just want to not have every single thing that runs electricity on in my house at the exact same time, then I can run one device and leave the other one off. So I don't have to turn on my microwave and my dishwasher just to have my refrigerator running each day. So that is it for electricity. If you have any questions, please feel free to email me and I can clarify stuff for you, or you can always go back to earlier in the video and rewatch.